to be laid out like this. First, I'm going to motivate the work before diving into some primers on lifted linearizations, Koopman operator theory, KIC and EDMDC, dual-faceted linearization, machine learning for learned lifting latent spaces, and anti-causal observables, so a lot of primers. And then next, I'm going to talk about some limitations in the state of the art. That will motivate a summary of the core contributions of my thesis, and then I'll dive into exactly what those are. Starting with the learned lifting linearization, or L3 algorithm. I'll show a numerical example of L3 at work in an experiment, and then I'm going to talk about something that we believe is not getting enough attention right now in the lifting linearization literature, and that is the problem of anticausal observables. And that will motivate the next two novel algorithms, the augmented and integrated lifting linearizations, or the AL2 and IL2 algorithms, and I'll demonstrate some experiments with those algorithms and then show an application of all three of my contributions using a simulated autonomous excavator experiment. And then finally, I'll conclude. So the motivation is that nonlinearity is everywhere in robotics. We have excavator terra mechanics, drag forces in underwater robotics, contact, non-contact transitions and manipulation, and of course, of particular interest to the Darbeloff lab, unidirectional load bearing in cable-driven systems. Folks doing research in these fields will tell you that these nonlinearities make our lives as engineers a lot harder. And in the feedback control textbook that every MIT Mechie control student reads, the authors write, quote, nonlinear equations are much more difficult to solve than linear ones, and the kinds of possible motions resulting from a nonlinear model are much more difficult to categorize than those resulting from a linear model. It is therefore useful to linearize models in order to gain access to linear analysis methods, end quote. So being able to linearize a system gives us access to a suite of tools to determine system stability, perform steady state error analysis, and optimally control the state. Oops. There we go. We can accomplish some pretty amazing feats with linearization. So Boston Dynamics dancing robots are just one of my favorite examples of linearizations being used to accomplish some pretty spectacular engineering feats. It's a great music video. One particularly smart way to linearize a dynamical system is using a lifting linearization. And for those of you who may be unfamiliar with lifting linearizations, here's a quick example. Consider this second order system with two states, got x1 and x2. This system is obviously nonlinear, right? We have an x1 squared term in the dynamics here. Naively, we might just say, you know, like, well, this system is nonlinear, so I guess I can't use any of the powerful tools I just talked about that only work on linear systems. But what we can do is we can create a new set of variables, z1, z2, and z3, where z1 and z2 are just the states, and z3 is x1 squared. And interestingly, in this new third order state space, the system from above evolves linearly. Right? This equation at the bottom is a perfect, exact linear representation of the original nonlinear dynamical system. And we achieved that by lifting the state space using z3 equals x1 squared. Now, that's pretty cool, but as you can imagine, general nonlinear dynamical systems cannot be represented by exact linear equations of finite order, right? And this is where Koopman operator theory comes in. So Koopman operator theory says, given a system dynamics, x at time t+1 equals some nonlinear function f of xt, and really quick note that I've switched over into discrete time now. Koopman operator theory instructs that we define a vector of observables that are nonlinear functions of the state. We have eta equals g of x. And this is like how we defined z3 to be equal to x1 squared in the last example, right? Then we use the Koopman operator to evolve these observables forward through time as a linear system. And this is really powerful because, as we showed with the example, because the new system has been lifted using eta, it will behave more linearly. Oops. Sorry. However, the original Koopman operator has two major limitations. The first is that the theory is only applicable to autonomous dynamical systems. So the original Koopman operator theory does not allow for exogenous inputs, like if I have a controller acting on the system or some disturbances acting on the system, it doesn't allow for that. And second is that the exact linear representation requires an infinite dimensional Hilbert space, except for a restricted class of systems. And modern lifting linearization literature has come up with several solutions to these problems. For the problem of finding an effective finite set of observables, state-of-the-art techniques can be broken down into two broad categories. The first, the most basic Koopman method, applies a synthetic basis, like, I don't know, for example, like a bunch of polynomials, or a Fourier transform, or radial basis functions, or something like that to lift the state. Newer techniques like dynamic mode decomposition and dual-faceted linearization use physically measured observables, which may be functions of both state and control input. And I'll get to why that's important in a sec. But the way all these methods work is by identifying a bunch of observables from a nonlinear dynamical system and approximating the system dynamics using a linear system like the one here in the bottom right. Now, Koopman picks all of its observables to be synthetic functions of independent states, right? So that means it measures all the states of a system and then computes a large basis, like maybe just a bunch of polynomials of the states or a Fourier transform, or radial basis functions, or something else I talked about earlier, right? But the basis is purely synthetic functions of states only. But DMD and DMDC, the dynamic mode decomposition with control, is not as careful. It takes a bunch of physical measurements from the system that may just be functions of state, but it might also be dependent on the control input. And this is important to remember because it will cause problems for us later. So dual-faceted linearization brings in the physical knowledge of the system by assuming that it is modelable as a lumped parameter system. Given system dynamics, state x at the next time equals some nonlinear function f of state and control input at the current time. DFL, or dual-faceted linearization, shows us how to choose physically meaningful observables such that we can approximate the state transition dynamics exactly with a linear model using a vector of physically meaningful observables, eta, right? That's this guy. Then we can compute a simple linear regression to compute a least squares estimate for a linear dynamic model for these eta dynamics. And the key point of DFL is to use the outputs of the nonlinear elements, like the nonlinear springs and masses and dampers in the system, like the one kind of shown here in this graph, as observables. And we can use the auxiliary variables to make the state equation, this equation right here, perfectly exact. Now, DFL is a powerful technique. It allows us to exactly linearize the state transition dynamics with a finite set of observables, and it provides a systematic method for choosing those observables, right? Namely, we lift the system with the outputs of all of the nonlinear system elements. It also provides a method that I'll discuss in more detail later to analyze the causality of those observables. But DFL also has some drawbacks. First, it requires knowledge of the structure of the system to work, but many systems contain no obvious physical observables with which to augment the state. Plus, physically meaningful observables may not be the best choices for modeling the dynamics. So the machine learning community has also developed several tools for creating linear latent spaces. Abraham and Murphy developed an algorithm a few years ago to actively learn dynamics of a system using Koopman operator theory. Their model assumes linear state feedback can be embedded into the original system, which limits their applications to regulator problems, but regulator problems are still important. They train a neural network to model the dynamics directly, and in each epoch, they recompute a finite dimensional matrix approximation of the Koopman operator K. However, because regressing requires knowledge of future values of control input, causality issues prevent like truly broad exogenous application. Han, Hao, and Vaidya developed a deep learning algorithm for a Koopman representation of dynamical systems. They also train a neural network as a kernel with which to lift the space. And in each epoch, they regress a modified eta transition dynamics and then back propagate the modeling error through their neural network. However, their algorithm doesn't track the evolution of state X, so instead it learns an additional matrix to approximate the inverse of their neural network G. The reinforcement learning community has developed several algorithms to learn linear latent spaces. They don't explicitly mention Koopman operator theory, but the math ends up actually being very similar. However, their learned linear models are often time or state dependent, which means that they are only locally linear and not globally linear like DFL or Koopman methods. So now, gone through all of the kind of the primers that are necessary for right now. So let's dive into my first core contribution of this thesis. At its core, the learned lifting linearization, or L3 algorithm, consists of a neural network, that's G, that takes state inputs, that's X, and outputs a set of nonlinear observables, eta. This output, the state and the control input, are fed through a linear dynamic model that evolves the state forward through time. That's the core of what the L3 algorithm does. But how do you train something like this, right? Well, we want to use a supervised learning paradigm. So we need, kind of quote unquote true values of X and eta at the next time step. And so X at time t+1, that's just going to come from data. We're going to measure it. And we create a dual copy of the neural network G to create a kind of quote unquote true value for eta at the next time step. Then we use a cost function J to compare the true values to those generated by the linear dynamic model. So we're comparing X hat and X at t+1 to eta hat and eta at t+1 using the cost function J. And then we're going to back propagate the error through the neural network and the linear dynamic model to update the parameters. Now, there's two options to train the L3 algorithm. The first is using a least squares estimate. And the way this actually works in practice is by using a bootstrap method. So what we're going to do is we're going to fix theta. We're going to fix all of the neural network parameters. And then we're going to use a least squares estimate to regress and update for the linear dynamic model parameters A and H. And then we're going to fix A and H and then update the neural network parameters eta. And we're going to kind of go back and forth, updating the parameters back and forth a bunch of times. And the reason we have to update them back and forth instead of just doing them all at once is because if we're using this least squares regression, right, this least squares estimate for the linear dynamic models A and H, these matrices A and H are going to be functions of theta, which make the which would make the gradients with respect to theta very, very complex. That's why we have to fix theta and use this bootstrap method if we go with the LSE route. There's another thing we can do is just treat everything and update everything using error back propagation, right? So we can treat the linear dynamic model as a separate output layer to the neural network. We can just kind of like tack it on as a linear output layer and then train everything, the linear dynamic model parameters and the neural network parameters via back propagation in tandem with all of the other weights. This method is more computationally efficient, and what we found is it actually also produces better results, which is kind of cool. So next, I want to be able to provide my neural network with more information than just state alone. And I would like to also give it those physically measured observables, kind of like DFL does. I want to take advantage of that extra power from DFL of being able to measure physical observables and use those in my model. But there's a problem. Outputs measured from the control system may be functions of not only independent state variables, but also inputs, right, that are exogenous. And if one uses the output as an observable for lifting the space, right? If you use phi, which is a function of both state and control input, then their time derivative of that observable is going to include the time derivative of control input. And when you represent a time derivative in discrete time, that requires knowing future values of input. And if this control input U is truly exogenous, we can't know any future values of it. So this is an anti-causal problem, right? This is anti-causal lifting. Now, you can solve that problem by including a state feedback control law in your model, right? You can say that the control input is dependent on the state, and that basically reduces the problem back to the original Koopman operator theory. And that's nice, but you sometimes want to model systems with inputs that are truly exogenous, right? So DFL proposes another solution to this problem that assumes the observables eta are linear in U. And then you can just subtract out the effect of the control input on your observables and track this new synthetic observable eta star instead. And this eta star right here, right, is exclusively a function of states. You're not going to run into that causality problem. So basically, this first method, it works, right? But it limits the scope of your application to regulator problems. And also the function U of X has to be known and fixed. And the second solution, right, this one, is more broadly applicable in terms of applications, but the linearity assumption is limiting in and of itself, right? It's going to be inaccurate in the presence of strong nonlinearities. So the learned lifting linearization algorithm can also include physically meaningful observables gathered from measurements using that causality filter, that second solution, similar to DFL. So I'm going to call physically measured observables that might be functions of control input U. I'm going to call those zeta, and I'm going to assume that zeta equals the sum of some nonlinear function of state, that's going to be zeta star, and some fixed parameter D times control input U. Now what's cool is after I mean zero the data, because zeta star is uncorrelated with input, the expectation of zeta star times u is going to be 0. And we can use that fact by post-multiplying both halves of this equation at the top by u transpose and taking the expectation. And what that does is, because this expectation is 0, this middle term here drops out. And we can now solve for D, an optimal least squares estimate for D, using just like a basic simple least squares regression. Now that we know D, we can subtract D times U for each physically measured value of zeta, right? And then use this cleaned, filtered version of zeta in the neural network to augment the state and provide more information about the system dynamics that we can use, importantly, to regress an optimal linear dynamical model. So here is the full L3 algorithm, right? We have a state and a cleaned version of the physical measurements eta star are fed into the neural network. The output of the neural network and the state and zeta star and U are all fed into the linear dynamic model. And a twin model on the other side provides a, quote unquote, true values for all the important variables so that we can back propagate a modeling error and continue learning a better model for neural network G and linear dynamic model A and H. So I implemented the learned lifting linearization on a simple numerical model of a massless spring damper, kind of shown here as a bond graph. And don't worry, just in case you're unfamiliar with bond graph notation, I've also pictured it here as a fixed wall connected to a massless plate by a nonlinear spring C and a nonlinear damper R, and a force input acting on the massless plate, that's U. The position of the plate is represented by the state Q. Now, DFL teaches us to lift the system using EC, which is the force applied by the spring, and F, which is the force applied by the damper, which also happens to be the velocity, or sorry, not the force applied by the damper, the velocity of the damper, which also happens to be the velocity of the plate. But herein lies the problem. F is obviously important as a lifting variable, right? Like it literally equals the state dynamics, right? But F is a function of control input U. So when I try to lift the system using F, I end up getting an equation for F dot that includes the time derivative of control input, and that's anti-causal. So that's why we need the anti-causality filter. So in this experiment, I want to benchmark the learned lifting linearization algorithm against the state of the art. So I choose Koopman with inputs and control, which applies a synthetic polynomial basis to just the state variables, not the measured observables, and then regresses a linear model. I also use extended dynamic mode decomposition with control, which applies a synthetic basis to the state variables and the physical observables and regresses a linear dynamic model. And then finally, I also use dual-faceted linearization, which does almost the same thing as DFL, but also applies the causality filter to clean the physically measured observables first before using it in the linear dynamic model. All right, and these are our results. So let me walk you through it. The black line, right, shows the true system trajectory given a square wave control input. The worst performing model, unsurprisingly, is EDMDC. So that's the cyan line. It lacks the causality filter, and because of this, it completely fails to track the system trajectory. The second worst algorithm is the only other algorithm on this list that both incorporates the physically measured observables without first filtering out the effect of control input. And that's the magenta line. That's a version of L3 of the learned lifting linearization algorithm I created that lacks access to the causality filters. That's L3 no filter. It can use the neural network, and so it performs a little bit better than EDMDC, but it still fails to track the system well. So the next algorithm is Koopman with inputs and control. That's the green line. KIC's solution to the anti-causality problem is just to ignore the physically meaningful observables altogether. But even ignoring these important data, right, it still performs better than EDMDC, right? And then there's DFL in red, which regresses a linear model that does actually try to filter out the effect of U on the physically meaningful observables. And DFL does relatively well. But finally, when we add a neural network onto DFL to get the learned lifting linearization in blue, we actually achieve like a solid, robust tracking of the ground truth trajectory. And keep in mind, all of these simulations are open loop, right? At no point in time after the initial condition are these tracking algorithms given access to the current real state. It's all done in open loop. We also did an experiment to actually test to see kind of like what the difference is between the least squares estimate and error back propagation testing algorithms, the training algorithms for the L3 algorithm. And this is more just kind of like a side note. I just found this interesting. The LSC method and the EBP method, the error back prop method and the least squares estimate method, actually do come up with substantially different linear dynamic models. This isn't anonymous. This isn't like anomalous or surprising, but it is. I did find this interesting that these two training methods actually do come up with very, very different algorithms. Okay, so what happens when we increase nonlinearity, right? Well, recall that the way that DFL and L3 deal with the anti-causality problem is by applying a filter to remove the effect of exogenous input from the physically measured observables. However, this filter assumes that these observables are linear functions of input. And this assumption is limiting. So here's another example of a system with anti-causal auxiliary variables. I'm going to give you a second to try and spot where you think the causality problem is. So see if you can do it now that you so fully have a grasp of this anti-causality problem. Right there. So the Q dynamics include a nonlinear function of exogenous input, UE1. And I know I could have made this easier by showing you the vector observables, but I know you don't need it at this point. So to better examine the signal paths from input to observables, I'm going to convert the icon model into an element block diagram. And the first thing we want to note is the mass. So it is the job of an inertial element to convert effort variables, like forces, into flow variables, like velocities. And crucially, it doesn't go the other way around. This causal flow analysis comes from Newton's Principia, in which Newton points out that force determines the future motion of a mass and not the other way around, right? And this kind of makes intuitive sense. If I were to throw a ball, we wouldn't say that the projectile motion of the ball caused me to throw it, right? We would say that the force from my throw caused the ball to fly through the air. And this gives a specific direction of signal flow, right? Inertias convert forces into velocities. And the reverse argument can be made for capacitive elements like springs that convert flows like velocities into efforts like forces. So and another way you can look at this is by thinking about what is actually computable, right? If the causal path were reversed, then the integral block would turn into a derivative block, which, like we talked about earlier, would require knowledge of future values of the input, and that would be causal. Resistive elements, though, like dampers, are different. Unlike springs and masses, resistive elements don't store energy and don't have an internal state like displacement or momentum. And their statelessness can kind of create a problem. So when you use the output of an inertial element, the velocity, to lift the system, the derivative is going to be a function of the derivative of the state of that inertia, right? That's this first equation. And likewise, when you use the output of a capacitive element like a force to lift the system, the derivative is going to be a function of the derivative of the state of that capacitor, right? However, because resistive elements like dampers have no state, their dynamics might be functions of time derivatives of input. And this means that only systems with resistive elements can have anti-causal observables, and only observables associated with those resistive elements may be anti-causal. So with that, let's return to our example. DFL instructs that we lift first with E sub R2, which is a function of momentum P. So that's fine. No causality problems there, all is well. However, DFL also instructs that we lift with F1. But F1 is the output of a resistive element whose input is a function of the left exogenous input. And that's going to be a big problem, right? That's why we identified this as a system with anti-causal lifting dynamics. But this is just an example system. Taking a step back, in general, there are two ways that auxiliary variables can become anti-causal for lifting. The first is if a resistive element is connected via a loop junction with a subsystem whose output includes an exogenous input U. So, and by a loop junction here, I just mean a way of connecting subsystems. So it's the generalized Kirchhoff's loop rule, where all the subsystems share a common flow, and all the efforts of the subsystem sum to zero, governs the dynamics. There's two subcases for which this is true. If the resistor is connected to two flow-to-effort subsystems via a loop junction, like subfigure A on the left, or if the resistor is connected to an effort-to-flow subsystem via a loop junction, like is shown in subfigure B on the right. So the second way auxiliary variables can become anticausal for lifting is if a resistive element is connected via a node junction with a subsystem whose output includes an exogenous input U. And here by node junction, I just mean a way of connecting subsystems such as the generalized Kirchhoff's node rule, where all subsystems share a common effort and the flows all sum to zero governs the dynamics. Just as before, there are two subcases for which this is true. If the resistor is connected to two effort to flow systems via a node junction like subfigure A on the left, or if the resistor is connected to a flow to effort subsystem with a node via a node junction like subfigure B on the right. So let's start with the node junction. I have to find a way to prevent these causal paths from connecting the subsystems, which may include exogenous input, to the resistive auxiliary variable. So the first thing I'm going to do is I'm going to break off one of the subsystems so that I can add in some block in between it and the resistor that will purge the exogenous input from the signal. Let me clean up the lines really quick. Great. So I need something that will take the contaminated flow output from the subsystem and convert it into a clean state variable dependent effort. And what tool do I have that converts anti-causal flows into causal efforts? What tool do I have? I have a capacitor, right? A capacitor converts flows into efforts. So returning to my block diagram, I'm going to augment the system with the capacitive element placed in the system node junction as the resistor and subsystems. And cleaning up the diagram a little bit gives me this, but I see a problem. If the resistive element maintains its causal path direction, then both it and the capacitor will be dictating the same output effort B, E. But that's a contradiction, right? I can't have two elements independently outputting the same force. That would be a short. Thankfully, as I discussed earlier, because resistive elements don't have an internal state, their causal path directions are dictated by their configuration with respect to the other elements in the same junction. So to solve this problem, the resistive element must reverse its causal path. Instead of converting a flow to an effort, because we added the capacitive element, the resistor now converts an effort into a flow. And that auxiliary flow variable is a function not of exogenous input, but rather of the capacitor's internal state Q. And we can apply a similar fix for causality problems pertaining to resistors in loop junctions. However, instead of needing an element that converts flow into effort, right, because that would just get absorbed into the flow to effort subsystem, we would use an element that converts effort into flow, and inertia. And as before, the augmentation of the inertial element into the loop junction severs the causal path from exogenous input to auxiliary variable by reversing the causal path of the resistive element and ensuring that the lifting variable E is a function exclusively of independent state P. Now, a few notes on this algorithm. First, the added inertial and capacitive elements may be linear. There's no need to augment the system with like some crazy nonlinear masses and spring. That's unnecessary. And if you keep them linear, then their outputs F equals the flow output equals state P over mass M, and effort output E equals state Q over capacitance C need not be auxiliary variables because they're just linear functions of states. Second, small values should be picked for mass M and capacitance C. Because this is changing the state dynamics of the system, right? This is changing things, and we don't want to change things too much. So we want whatever we're augmenting the system with to be small, such that it only helps the causality problem and it doesn't actually affect its system dynamics. And you can use Bode plots of the linearized system to help pick these values. 3, the added inertial and capacitive elements may be added anywhere in the system to break the causal path from exogenous input to lifting variable. It doesn't have to be in the exact same junction, right? It can be somewhere in one of the two subsystems. All this this augmented inertial capacitive element has to do is sever the causal path between control and exogenous input and and the auxiliary variable. And then lastly, remark 4, if the resistive element is directly driven by an exogenous input, right, like E equals phi r of u or F equals phi r inverse of u, it's not actually affecting the state dynamics, right? Like these are not functions of state at all. So you can just omit this output from the lifted model altogether. So to summarize, the augmented lifting linearization algorithm instructs solving problems pertaining to anticausal variables in loop junctions by augmenting the system with a small inertia, and solving problems pertaining to anticausal variables in node junctions by augmenting the system with a small capacitance. And this is powerful, but as some of you undoubtedly noticed, applying the augmented lifting linearization requires altering the system dynamics of the system by pretending that it includes elements, even small ones, that it doesn't actually include. It changes the dynamics, right? And what I would like to have is a method that solves the causality problem without altering the system dynamics. And to do that, I'm going to take a step back and think about why, mathematically, the augmentation of an inertial or capacitive element to the system actually stops the exogenous variable from reaching the auxiliary variable. So the block diagram, or sorry, the block that prevents this red line, right, from reaching the auxiliary variable E is the integrator block. It is by integration that the anticausal variable EI is transformed into an independent state variable P. So let's just use the integrator block to lift anticausal auxiliary variables directly without altering the system dynamics. So let's say that we have a super general dynamical system with a resistive element whose auxiliary variable is contaminated by an exogenous input. And instead of lifting the system dynamics using this auxiliary variable, I'm instead going to synthetically measure its integral and then use that to lift the model instead. More formally, for each auxiliary variable of a resistive element that is a function of control input u, I want to replace that observable with the integral of itself. And then when I go to lift the system dynamics using that variable, instead of applying the chain rule and getting a time derivative of exogenous input u, I just get back the original observable. And that way, I can lift the dynamics causally without altering the system dynamics. However, there's one caveat. In some cases, phi star is already included as a state variable. So for example, consider the system given by x dot equals some nonlinear function f of u and es, where es is a nonlinear function of state. You'll probably know the next steps by now. DFL instructs lifting with f and es, but f is a nonlinear function of exogenous input u, and therefore cannot be used for lifting. However, the integration of f based on this integrated lifting linearization algorithm is the same as state x. And therefore, the integrated auxiliary variable does not make any meaningful contribution. So the IL2 algorithm just instructs ignoring f altogether. Okay, so I've been talking a lot of math for a while now. Now I'm going to get into a simulated experiment. And I'm going to start with a simple numerical example with 2 states, that's P and Q, 5 observables, those are listed here, and 1 control input, that's U. And as you can see, this observable right here is a nonlinear function of my exogenous control input, which means I can't use it for lifting the system. And even if you had never met me before today, by now you know that there is nothing I despise more in the world than an auxiliary variable that is anti-causal for lifting. So I'm going to apply my new algorithms to clean the system from anti-causal lifting variables. The augmented lifting linearization algorithm here on the left recognizes that the resistive element is connected via a loop junction, and therefore augments the system using a small linear inertia with state P star. Effectively, this replaces our anti-causal observable with a new observable function, a new nonlinear function of our new state instead of the exogenous input, and it augments the system space with the dynamics of our new state, that's P star, right? The integrated lifting linearization is a bit simpler. It simply instructs replacing the anti-causal observable with its integral. And one thing to note is that due to the augmentation of the additional state in AL2 that is absent in IL2, the AL2 model is of slightly greater dimension, right? We have 1, 2, 3, 4, 5, 6 observables in AL2 and just 1, 2, 3, 4, 5 observables for IL2. We benchmark AL2 and IL2 against the same algorithms as before, and I show the plot of the sum squared error across both states. As before, the DMD-based model fails to track the system at all due to its causality problems. And this time, interestingly, the Koopman algorithm is also so poor that it performs about as well as EDMDC. Interestingly, the additional nonlinearity in this model relative to the last experiment, quickly breaks the linearity assumption inherent in the causality filters used by DFL and L3 models. So L3 appears to learn a decent basis in spite of this, but its performance barely beats the Koopman and DMD models. Whereas on the other hand, the augmented and integrated lifting linearization algorithms achieve substantially lower tracking errors than any of the state-of-the-art systems. And IL2 especially is able to track the system accurately over a pretty long period. But this is just one example with kind of moderate nonlinearities. I used signed, quadratic, cubic, and quartic functions for the constitutive laws, phi c, phi r, and phi I. But next, I'm going to increase the nonlinearity by replacing them with highly nonlinear cubic functions, 3x cubed minus x. And I'm going to run the experiment 10 times with new and random control input signals to see what happens. And when I do that, the new nonlinearities are in such extreme violation of the assumption made by the linear causality filter of DFL and L3 that both just like immediately go unstable. So I've excluded them from the graph because their errors are basically infinite. As before, EDMDC can't track the system at all, right? And the Koopman-based technique does an okay job because it omits the anti-causal lifting variables altogether. AL2 and IL2 achieve the lowest sum squared tracking error. And for me, this graph is like the core result of this contribution. In the presence of extreme nonlinearity, when no other algorithm is capable of causally filtering and linearizing a dynamical system, the AL2 and IL2 algorithms perform substantially better than the state of the art. Okay, but if you were listening closely to my presentation on Koopman with inputs and control, or KIC, you might be asking yourself, like, what is so special about these algorithms? Like, why couldn't you just design a synthetic KIC basis to emulate AL2 and IL2? And if that's what you were thinking, this slide is basically like me tipping my hat to you. On one hand, you're kind of right. In one sense, like all I've done is like point out like some smart ways of effectively lifting a state space. But I think that there's something more to this. Much of the literature on Koopman operator theory admits that observable selection is very important, but KIC does not offer an algorithm to select these observables. DFL-based methods do, right? That's using the outputs of auxiliary variables, and that's something really powerful that you get from DFL. Secondly, to my knowledge, no Koopman-based algorithm has ever before prescribed using integrals as a key component of your observable functions. And as I discussed previously, the integrator blocks are what allow AL2 and IL2 to succeed. Now, the experiment on the right here is just a small exploration of these points. So instead of just showing one polynomial basis like I have for previous experiments, I show several polynomial and Fourier bases with different dimensions to demonstrate the futility of kind of picking quote unquote smarter bases for your Koopman algorithm without using your knowledge of system structure and causality, right? And in this experiment, switching from a polynomial basis to a Fourier one did improve results slightly, but even quadrupling the size of these models couldn't achieve the performance of AL2 and IL2, which, as you remember, use bases of dimension 6 and 5 respectively. So basis selection using AL2 and IL2 substantially improves the model without drastically increasing the order of the model. So there's one more benefit to using DFL-based methods that Philippos Soteropoulos explored in his dissertation, using physically measured observables of state instead of synthetically computed functions of state gives you better performance in the presence of noise. Because DFL helps you choose observables that you can physically measure, the noise in your observables is uncorrelated with the noise in your state variables. And because KIC, on the other hand, synthetically computes its observables from measurements of state, there is no guarantee that the noise affecting one observable will be uncorrelated with the noise affecting another observable. So in practice, this means that DFL's performance diminishes only slightly in the presence of noise, whereas KIC's performance degrades substantially faster. One more thing before we dive into application. I mentioned earlier that there are some cases in which IL2 doesn't perform that well. And one of those cases is when the integral of the anticausal auxiliary variable is actually just a state variable I already have access to. So I constructed this simple numerical example with just one state Q and two auxiliary variables. As you can see, the last observable here, right here, phi r of u minus phi c, is a nonlinear function of exogenous input u. But when I apply IL2, I find the integral of that observable is just the state, right? That's just q. So I ran the simulation 100 times with random input signals, and I noticed that because IL2 instructs that we simply omit an important piece of information, that's that last observable, right? The augmented lifting linearization actually outperforms it most of the time. As shown in the CDF plot here, the median sum squared error of the AL2 algorithm, right here, is much lower than the median sum squared error of the IL2 algorithm. Okay, so next, I'm going to apply all of my algorithms to the task of autonomous excavation simulations. First, I'm going to show you all a data-driven experiment, which will show off the learned lifting linearization because DFL, AL2, and IL2 require a model, and therefore they won't be present in this data-driven experiment. And then I'll show a model-based experiment that can include the new algorithms. So for the data-driven experiment, I worked with Philippos to generate a bunch of training data using a multi-physics simulator called AGX Terrain. We simulated gravel terra mechanics on an excavator bucket with a collection of states like position and orientation, and a bunch of physically measurable observables like the mass of the soil in the bucket and the force of the ground on the bucket. And then we applied the learned lifting linearization to see if it could predict state trajectory over time. And sure enough, compared to state-of-the-art Koopman and DMD-based lifting linearizations, the L3 algorithm was better able to predict the trajectories of state, that's this top row, and physically measured observables, that's this bottom row. We also tested the L3 algorithm without the anti-causal filter, that's this magenta line here, and of course it quickly failed, right? Providing more evidence that L3 succeeds because of a combination of neural networks and causality filtering. It really needs both halves of that equation. I also designed a model-based autonomous excavation experiment so that I could test AL2 and IL2 on a version of the hydraulic excavator model in Professor Asada's original DFL paper. Here I show the bond graph of this model hydraulic excavator system, along with 3 states, that's PQ and R, and 5 DFL auxiliary variables here. And just as before, I simulate the models 10 times given random input trajectories. And this time, something interesting happened that, if I'm being honest, I did not fully expect to happen. Even though both AL2 and IL2 outperformed KIC and EDMDC, AL2 beat IL2 by more than a factor of 2. As for why this is, hypotheses non fingo, I offer no hypothesis as to why AL2 beats IL2 in this scenario. And I personally think that there is some interesting future work to explore here to determine exactly when each algorithm should be applied. So to conclude, here again are the 2 big problems for Koopman-based lifting linearizations. First, how to find an effective set of observable functions that are finite in number. And second, how to model systems with exogenous inputs. I use neural networks and deep learning to solve the first problem, and I use bond graph theory and physics-based system modeling techniques to solve the second one. The contributions of my thesis are threefold. Method 1, a general algorithm for modeling nonlinear systems using a learned lifted linearization with the ability to filter out anti-causal auxiliary variables. Method 2, causal modeling of nonlinear system dynamics via integration and inertial augmentation to repair anti-causal auxiliary variables. And finally, an application, a case study of these methods applied to autonomous excavation models. Before I open the floor for questions, I would like to thank my PI, Professor Asada, for your patience and your motivation and just your amazing scope of knowledge. I've learned so much during my time in your lab, and your guidance throughout my PhD journey has been invaluable. Likewise, to my committee members, Professors Lozano Perez and Agrawal, thank you for serving on my committee and for offering your expertise and your mentorship. My dissertation, it would not be the same without you. I was blessed with a social and intelligent group of lab mates. Thank you all so much for welcoming me so wholeheartedly into your group. I also want to thank my family, Tom, Lori, and Lucas. I definitely won the family lottery. Your support and love made me the man I am today. And lastly, Anne, my partner, I love you. Thank you for your immense support throughout this process. And I look forward to supporting you through your own doctoral studies. And with that, I would like to open the floor for questions.
Okay, thank you. Yeah. So I'm not so much sure about the ECS doctoral defense, and so I asked the Thomas how we can run it. And according to Thomas, the first session of the Q&A is mostly for questions from the audience, not the committee members. So I'd like to take some questions or any comments, whatever, from the audience other than the committee members. I think, am I correct, Thomas?
Yeah, that's right.
Okay, go ahead.
Would you mind, I can't see who's raising their hand. Would one of y'all mind picking people to ask questions?
Yeah, go ahead.
Thank you so much.
Or whatever. Or everyone can unmute.
Oh, perfect. That works too.
Yeah, John Bell, go ahead.
Yeah, so looking at the main assumptions that go into whether this theory is applicable for a model, one of the things that I guess kind of popped out to me is that the lifted state variables, or the latent lifted variables, sort of have to be related to the other ones by virtue of being added. So you could have an x variable and an I think a eta variable or a phi variable.
Right.
And ultimately your dynamic equations have to be the form of some constant times x plus some constant times eta. If your dynamics were multiplicative, so you had a fundamentally bilinear system, x times eta, would this theory just not work? Are there some workarounds?
Yeah, that's a really good question. So so one quick asterisk on that, John. The structure of the nonlinear constitutive laws, right? So the outputs of these nonlinear elements, like the force output of the spring or the damper, or the inertial elements in these systems, even if they're nonlinear, those can be multiplicative, and that's fine, right? But the inputs to those constitutive laws have to be governed by Kirchhoff's, either generalized Kirchhoff's loop or node rules, right? And that's why you see so many kind of pluses and minuses separating the control input U and the state variables X, right? So as long as your system is a lumped parameter model, right? As long as your system is in general governed by these generalized Kirchhoff's loop and node rules, no matter what the structure of your nonlinear constitutive laws are for your nonlinear elements, you can apply the augmented and lifting linearizations. Now, keep in mind, though, the learned lifting linearization does not have to rely on a model. It definitely helps if you use DFL and these lumped parameter models to select causal auxiliary variables. But in the application here, right, we didn't have that. There was no bond graph. We did not assume that these crazy Terra mechanics were a lumped parameter system, and thus, but we could still apply the L3 algorithm.
Okay, so I guess a follow-up is that, so the mathematical robustness to what you're working with so it's, from what you said, it seems to largely result from the fact that your systems are based on energy flow and conservation?
Yes.
Okay, so if that were not the case, if it were just some like other dynamics model that's not based on energy, these guarantees kind of get thrown out the window.
Yeah, or you could just, I mean, like, so for example, if you didn't conserve energy, right? If you had some like external energy coming in, then you would just model that as another exogenous input.
Well, thanks.
Yeah.
If someone else has a question, they should raise their hand on or unmute.
Yes, please.
It was so clear, they're all stunned.
Yeah, we'll go with that. Yep.
Jerry, go ahead.
Wait, what? Oh, am I allowed to ask a question?
Tear me apart, Jerry.
Okay, yeah. So kind of related to John Bell's question.
Yep.
How could this be applied to something like modeling financial markets where things are not energy conservative at all?
Yeah, I think sorry, Jerry is like a financial wizard, so this is a fun question. I think that if you were going to apply this to financial markets, often probably what you'd find is that the stock market is not modelable using bond graphs, or at least I have not particularly seen a way that you can do that effectively. So I think you would have to apply some kind of like machine learning basis similar to L3. Also, I'm not sure the amount of money that you would have to have in your investment account would have to be extremely large in order to be able to be considered like a real exogenous control input. So that you might be able to get away with just kind of like OG machine learning Koopman representations.
Nice. Thanks.